got the letter saying that you have a talk, not a poster for this, I went online and saw that I have a 15-minute talk, and then when I got here and looked at the schedule this morning, I saw it's 30. Yeah, okay. So, but my talk tomorrow is only 15. So I have, I put in 2 extra slides this morning, and the first one is on being JGR space physics editor. And so I just like to, say that I started this blog because digital publishing has changed a lot in the last 10 years, and it's going to be continuing to change over the next few years. And so to help make that start a dialogue between the editorial board and the community, and also just to make people aware of these changes that are going to be rapidly coming over the next few years, I thought I would create this. And just from, but today's was more statistical, so I just thought I'd share with you a couple of those points. One is that you guys write a lot of papers. 1,000 a year, roughly, come in. And, that's actually pretty high. We're only behind a couple others in terms of how many manuscripts come in each year. Of that, about 70% end up being papers in the journal. So Bob Lysak and his crew have had about that acceptance rate for the last couple of years. And what you could take away from that is that we write good papers in general, because this is not beyond the norm, but it's above average among the AGU journals, especially compared to that other one that Bill is one of the editors of. It's about double the acceptance rate of that journal. So usually people submit to JGR Space Physics, they're submitting a paper that is well written and has some significant new original result that is worthy of publication. And finally, this last point that I'd like to make that really makes me proud to be a member of the space physics community. We're really good at getting reviews in on time and under budget and all that other comments. Not that we have one of the fastest acceptance rates, and the only journals faster are GRL, which is supposed to be fast, and Space Weather Journal, which is our journal too. Yeah. So I better not. But I'd like to say, it's only a little bit me. It's the community that's doing this. It's you being willing to accept reviewer assignments and saying yes when you clicking the accept button, not the decline. It's you being willing to write a thoughtful review so that the decisions come back and papers go through the system quickly and easily. And it's you writing timely reviews and getting them done by the deadlines assigned, or at least within a week of those deadlines. And really, the long or the long lead time, or the really tiny review or something like that, those occasionally you'll see those, but those really are the exception, not the norm. And so everyone, just reach over and pat yourself on the back. It's a really nice. You make my job easy. Yeah. I might, because, some people piss me off. Okay. And it's only been 2 months, and I'm already, that's it. Yeah. Okay, so on to MHD modeling. So we've heard a lot about ionospheric outflow, but, just how important is it? And so one way to look at that is with the observations like what Lynn Kistler and others have been showing us earlier tonight. But I'd like to approach it from a numerical standpoint and do some simulations with an MHD code coupled to an ionospheric potential solver, just those 2 codes in the solution, but using a multi-fluid approach so that we have one fluid that's coming out of the ionosphere as its source term, and the other fluid with its source term at the inflowing boundary of the solar wind. Both of those are H+, by the way. It's only a 2-fluid multi-fluid calculations. I'll also show a little bit of multi-species results near the end. So these are going to be idealized runs. All I'm doing is flipping the IMF from southward to northward. And so we're going to look at the southward case, we're going to look at the northward case, and see just how much ionospheric material contributes in different places in those 2 simulations. And Dan Welling had a paper on this a few years ago, but that was multi-species. And there is a interesting difference here that I'd like to point out at the end about about the difference between multi-fluid versus multi-species. So I'm going to be showing you some plots that look like this. Red is solar wind dominant in terms of number density, and blue is ionospheric dominance in terms of number density. That's the main thing you need to know. And that green is right at the middle, the 50% mark. Okay? Slices in the meridional plane as well as in the equatorial plane. We'll be looking at some of those as well. Okay? So wrapping your head around this, there's the simulation picture. So here, this is for, do we have a, here we go. Okay. If I can find the button. Meridional plane ionospheric dominance going all the way out to more than 20 Earth radii, all the way out to the reconnection zone in the back. In the equatorial plane, you can see a little more carefully about what's actually happening here. The ionospheric dominance is not everywhere. It's only in the central part of the tail. That the outflow comes and it hits the magnetosphere, but the solar wind is creeping in on the flanks and populates the flanks of the tail pretty significantly. It's not contributing much to the number density here in the inner zone, in the inner magnetosphere in these simulations, but it is there is significant solar wind within the tail coming in through the sides. Northward IMF, totally different situation. Again, you look at this and you say, wow, look at all this solar wind coming into to the tail. It's not coming in across any sort of night side boundary. It's coming in on the day side through double lobe reconnection. So it connects on one, connects on the other. This is how it's happening in the code. And it slips across the day side, and by the time it gets right about x equals 0 or so, somewhere in this 0 to minus 10 range, it finds its way curling inward from the dawn flank, and a little bit on the dusk, but that doesn't make it in very far. The dawn flank is the one where it comes across these stream traces right into the near-Earth zone. So it's just gradient curvature drifting, gently flowing right across here, and the inflow bifurcates. There's a little bit that goes like right around the outside here, a lot that goes tailward across the tail on both sides, but right in here, the near-Earth night side region, dominantly solar wind material of stuff creeping in from the dawn side, slowly leaking in right here. And the ionosphere still contributes to that central tail. So there's still stuff coming out of the ionosphere and raining down on the plasma sheet from both north and south. But it's only in this narrowly confined region, and it's not a dominant contributor to the number density anymore, the way it was with southward IMF, where we're driving it. Another style of plot here that I'd like to show you, these are line plots across some particular x distance downtail in the equatorial plane, and then watching it go with time through the simulation. So the x-axis now is run time through the simulation, and the y-axis is y. So 0 right at midnight local time in the center, and then dawn in the lower half, dusk in the upper half across here. So in each one of these plots is a different distance downtail. So you can see solar wind dominance. What happened here? Southward IMF and then northward IMF. Sorry, you can't read that on this projector here. So southward IMF, it's reached steady state, and at time equal 4, we flip the IMF northward, and we watch to see how long it takes for the solar wind to do its inflow. And you can see there is some transient reconfiguration here of snapping and reconfiguring of the tail. Those are transient. They disappear. All this stuff goes down tail very quickly and doesn't contribute to inward. You can see that this does not really have too much coming in. What happens is that stuff creeps in from the flanks. And so you can see that pretty dramatically at 15 RE downtail, but even at 5 RE downtail. So you're out on the flanks here. So here's plus and minus 5. It's solar wind dominated all the way into the inner magnetosphere during northward IMF. It takes a while to get there, though. I guess that's the point of this, is that this turning happened at 4, and reaching some quasi-steady state, it's at least 4 hours into this run. So things are not driven during northward IMF very strongly. They're taking their time to move these ions around, but eventually you do reach solar wind dominance throughout the tail of the magnetosphere. This is the other slide that I put in after Halan's talk this morning, thinking about the asymmetry, because you could just see that in those previous plots. So I zoomed in on one of them, and just to show you, this purple line right here is the y=0 axis. During strong southward, this is -10 IMF hitting it, you can see that this is tilted a little bit in the dawn direction, and then the northward IMF, again strongly northward, +10 northward IMF, it's tilted a little bit in the dusk direction in terms of where the ionospheric dominance is happening. So here, basically symmetric, but maybe a little bit, ever so slightly off to the dawn direction. During the northward IMF, basically symmetric, but ever so slightly off to the dusk side. I'm not sure how that compares with you. You had it, disturbed versus quiet, but it was at a -20 DST level where you made that split. So I'm not sure where that fits in with this. -20 nanotesla DST could still be considered quiet depending on where you are in terms of a storm phase. So there could have been averaging of both of these lumped into that. So a big point here about multi-fluid versus multi-species to make is this plot right here. So multi-fluid, solar wind and ionosphere, red and blue curves on this chart. During the southward IMF, and this is at a particular point right down tail, so what's coming into the inner magnetosphere? What is flowing in? And what do we have? Ionospheric material during southward IMF, dominating the density. And then after northward turning, it hiccups a little bit, basically returns to the same level it was before. Ionospheric density is still coming in with as much density as it was before in northward or southward. The ionosphere is still producing the same density, either way. So when I say that the density dominance flipped in terms of southward to northward, in the simulation, it was entirely because this red curve skyrocketed. And so we had this extra source coming in from the flank, just slowly gradient curvature drifting right across the tail, and eventually reaching a much higher density than the ionospheric material. But the ionospheric material is still there, and still raining down on the near-Earth plasma sheet, and still providing as strong a density as it was before. Another interesting thing about multi-fluid versus multi-species is the temperature of the two. You can see here ionospheric material coming in at this region, 10 keV on average, or maybe 8 keV. That's about what we observe coming into geosynchronous orbit in terms of temperature, bulk plasma temperature. And but look at this solar wind, incredibly high. Where did this stuff come from? It didn't come from the flanks leaking in. This is actually, it's a really tiny density. It came in from that deep tail reconnection, or not deep, but -25. From the tail reconnection site and drifted inward, and it underwent the entire adiabatic acceleration from that reconnection line all the way up to -7. So it energized a lot on that, whereas the ionospheric material was raining down all the way across the plasma sheet, and so it has contributions from many different adiabatic energizations contributing to this temperature, this lower temperature. During northward IMF, things aren't driven, so you just have the solar wind coming in with the solar wind temperature, or velocity from the magnetosheath temperature, if you will, down here at like 1 keV coming in. And the ionosphere still raining down on the plasma sheet isn't driven in from deep tail, it's just coming in where it's drizzling. And so the density is still the same, but the temperature is much lower because it's not being driven in from deep in the tail. So this just essentially shows that, you know, where it hits in the plasma sheet, it'll undergo energization coming in, and if it hits deeper down, it will undergo more energization coming in. And so if it's happening at the reconnection site where the solar wind comes in, that's why you get this incredibly hot temperature here versus the ionospheric material, which can come in anywhere across the entire night side plasma sheet. So I think that's already shown right here. We have this stuff leaking in right here. It comes in across the side in order to populate this, whereas here, in order to get the solar wind material here, it started from here and underwent this entire distance of plasma sheet transport and energization across that. A final thing to note is southward to northward flip. This is a different simulation that we did at time equals 8 here. The IMF flipped from south to north, or sorry, that's backwards, north to south. And so this is south now, and you can see that it reconfigures into southward IMF within an hour or two. So the magnetosphere has two different time scales depending on what type of driving you have for how quickly it can reconfigure. We have to take that into account when we talk about time scales of convection within the system. So I think summarizing, you can get rather different temperatures of what's coming into the inner magnetosphere depending on where the source of this material is and just how much of the plasma sheet it underwent in its convection up. Thanks.
Gosh, I thought this was great, which is another way of saying it fits all of my preconceptions and prejudices
right. Yeah.
about what happened, how solar wind plasma comes in,
yeah.
and also how the ionospheric plasma gets redistributed. I had two questions, though. The first is, this morning numbers were thrown around like as much as, I thought, if I have it correctly, maybe 80% of the ionospheric outflow gets sent back into the inner magnetosphere. Mm-hmm. And I'm incredibly skeptical of that. So I'd just like to ask the question, have you attempted to determine how much gets sent down the tail by the reconnection?
I have not, but we could. That's a good calculation to do. Yeah, to compare against the numbers that have been thrown around this morning.
Okay.
Yeah, definitely. Yeah.
Yes. So the amount of...
I had one more...
Oh, go ahead. Sorry.
Oh, I see. I have one more question. It's short. It's not an opinion. It's just a question. The second point was I was also very impressed with how you captured the huge solar wind inflow that takes place during northward IMF. I didn't hear a lot of the jargon that we would normally hear if this was a purely magnetospheric conference, and I think it's kind of important. Because one of the many important discoveries that came out of the Geotail mission, which actually really startled us at the time, was that when the IMF is northward and it stays northward for a while, we see these super dense plasma sheets form. Mm-hmm. The plasma's cold, and by the way, that's magnetospherically cold. In other words, solar wind temperatures, not EV, not ionospheric temperatures. And we know that it's solar wind. We know that it's solar wind. We see even 4% alpha. So it's very clear it's solar wind. Densities get very high. Mm-hmm. The question for you, though, is the mechanism. I believe, and this is just my perception, that most people feel that it's Kelvin-Helmholtz at the flanks of the tail. The vortices roll up, and then they start reconnecting on themselves. And did you tell us it was KH? I didn't hear KH. Well, I know, but that's why I wanted to just...
Yeah.
So the two questions are, one, have you compared your results with the various Geotail, in particular the super dense plasma sheet results? And secondly, Does your
We get a
code-
super dense cold plasma sheet coming in at this time, and it is not due to Kelvin-Helmholtz
Okay,
along
and
the
you
flanks.
think it's great, is it in your, well, in your code, does your code, have you ever seen KH in your
Yes.
code?
Yes, we can
Okay.
get KH.
But it's not, is
We-
it just gradient drift? Or do you know what it is?
In terms of how the
does
KH,
how does the plasma get in from, at low latitudes on the flanks? Or is it all just going in through lobe reconnection?
yeah, lobe reconnection.
Okay, thank you. Thank you, that answered.
Yes, have you looked at the sensitivity? Oh. Were you
So
next?
close.
Microphone, I don't know.
Okay.
Next, Bill.
Okay.
Yeah.
You had about the third slide. You sort of showed your schematic of the magnetosphere and that kind of thing. Yes.
That'll work?
Okay. Okay. I am a little confused about that because is this a special case? Because the geotail observations show that the reconnection generally is way down tail, and you very rarely you get this kind of reconnection up close.
Well, this is southward minus 10 nanotesla IMF. So this is a pretty special case.
Okay. It's a special
I guess.
case as well.
Yeah, this is. I would say the geotail observations are
Okay. in
more so.
general,
When they're seeing that deep tail connection would be driven with a more standard IMF BZ of somewhere
okay,
plus or
if
minus
you're discussing
2.
a special case,
Yeah.
then I sit
Yeah.
down. I-
Okay. Yeah. Yeah. This is strong driving both southward and northward for these two conditions. Yeah.
Okay. Right, so the percentage of ionospheric plasma that's going to populate the plasma sheet and tail that you show here must depend to some extent on the nature of the outflow. Can you say something about
Yes.
how it's coming out?
Yes, good question.
The distribution of
Yeah.
where it's coming out and so
Yeah,
on.
this is so both of this run and the multi-species that we were comparing with have passive outflow, which means we assign a density at the inner boundary of the MHD simulation and no radial velocity. And the tangential velocity is applied by the electric field. And so within that first step, you get numerical diffusion, which might pop it off for a grid cell or two, and then forces within that first few RE of the
But Mike,
MHD drives it out.
I'm sorry to butt in, but could you address how much flux is coming out compared to other observed?
It's very similar to others, and there's a paper under review right now by Dan Welling on in analyzing this passive outflow source as a means of populating
You think
the
it's,
magnetosphere.
you know,
We think it's very reasonable.
Polar
Yeah.
wind-like or
Yes.
oxygen-like?
The patterns very much match what you would get with observations. Yeah.
Okay. I have a question.
The 10
Yeah.
to the 26 number kind of comes to mind, is that?
Yeah.
Yeah, and it's
Yeah.
very reasonable between a 10 to the 25th to 10 to the 26th number of what's coming out, with kind of standard numbers of, 10 to 30 AMU per centimeter cubed of a density at 3 RM at the inner shell that we're applying. Yeah.
So I have a hopefully provocative question.
I can get you that
Related.
manuscript of his that we have on exactly that topic. Yeah. Is Dan going to talk about that? No, I don't think so. I think he's talking about yeah. I think he's talking about also multi-fluid simulations.
Oh, I'm
right?
sorry, I missed
Yeah.
the question.
Are you going to talk about the passive source and how close it resembles reality?
I wasn't going to, but I could.
Yeah.
Okay, so my question is this. I'm going to butt in first. I'll
Okay.
be right with you, okay? But I just want to point out, I think, and you were describing how your boundary condition works.
Yeah.
It reminded me of Robert Wingley's boundary condition. That's typically how he does it.
Okay.
And I just want to point out that, to me, it seems like this pretty much agrees with, it appears to have reproduced to some degree Wingley's work, and in spite of all the grief he got at
Yeah.
first, I think it seems like he's somewhat confirmed or validated by this.
Yeah, I
Do
think
you agree?
he has similar results to this. I don't remember the specifics of his geopause calculations of density and pressure.
Thank you.
You know, yeah, those two. You wanted that word? Is that what you're hoping for? Yeah. Calculating those 3D surfaces of where there's dominance versus the other, and we could do the 3D surfaces out of this too, and that would be a good comparison against the Wingly plots.
Mike, I have a question, a comment, and then I'm going to take a liberty. Question, can you remind us what the difference between multi-fluid versus multi-species
Sure.
is? Because
Yeah.
I've forgotten.
Okay, multi-fluid is where you have complete sets of Euler equations for the different species. Multi-species is where you only have a density, a continuity equation for each of the species, and you have a single momentum and energy equation.
So that's the one where all
So-
the species are the same
So
temperature.
all the species move with the same velocity and temperature
Okay,
in
got it.
multi-species, but they each have their own density. Yeah.
Got
So.
it. And have you cleared that with Paramount? Because that looks like the Enterprise.
Oh, it does. Yeah. You're right. I could sell this.
And last, a little bit of an indulgence. As another editor, I'm the editor for JASTP. For my sins and for Bill Lotko. Yes, that other
Yeah.
journal. One of the requests, if ever you get a request to review a paper from JSTP, it's actually coming from me. And secondly, the most important thing is if you can't review it, decline immediately.
Yeah.
If
That's
the people who sit there and wait for 2 or 3 weeks to not respond puts a 2 to 3 week delay in the whole process. So that's my only request.
Yeah.
Decline
the request.
Decline the
immediately.
request.
Yeah. That's a really good point, and I think our community in general is pretty good about that. But it's a good reminder to make. Be prompt with those emails that you get from us.
I just had a small question.
Yeah.
So you have some asymmetry that you saw in the result. I was wondering if you included co-rotation in these simulations, and if that small dawn-dusk asymmetry may be due to co-rotation.
Don't think so. Yes, you're nodding.
Look at this. These microphones keep popping up. We do include co-rotation. Is the asymmetry due to that?
We're pretty far out.
Yeah, we're pretty far out. I don't think
Where we're
that's what's
seeing this.
driving it. And it's pretty uniform, too, if you look back to that plot that Mike showed. So we kind of are sitting on a set. Like I have the microphone. I won't shut up now.
I don't know
We have a
what plot
set
you
of
were interested
really interesting multi-fluid asymmetry results that we've yet to go through. It's really interesting. And one of the things I've seen is that if you expand this to 3 fluids, you see an asymmetry on one side for oxygen and on the other side for hydrogen.
Yeah.
And I don't understand that yet.
Is right. Yeah. I don't think it's co-rotation.
Any other